Good noon to all of you. Myself, Engineer H.S. Taliwal, Assistant Professor, the Department of Electrical Engineering at BHSPIT, Deragaga. So, today the topic of my lecture is tariffs and the power factor improvement. So, first of all, what is tariff? Electricity tariff, or sometimes it is also called the price of electricity. It varies widely from country to country, and it may vary significantly from the locality to locality within a particular country. So, there are many reasons that account for these differences in the price. It may be the government policies, it may be the market price of the fuel used, or the subsidies given by the government and industry regulation, and even the local weather patterns. So, tariff is the cost of the electricity which we are using. So, this is called tariff. So, next are the basis of electricity tariff. On what basis we are given the price, we are uh, considering the price of the electricity. So, electricity prices may vary all over the world, even within a single region or power district of a single country. So, in the standard regulated monopoly markets, they are typically varying from residential business and industrial customers, and for any single customer class it may vary by the time of the day or by the capacity or nature of the supply circuit. That is, we can use 5 kilowatt, 12 kilowatt, 18 kilowatt, 24 kilowatts are the typical loads used in the some of the countries. So, for the industrial customers, single phase and three phase supplies can be given. So, if a specific market allows the real time dynamic pricing, a more recent option in only a few markets to date, prices can be vary by a factor of 10 or so between the times of low and high system wide demand. So, what are the basic objectives of the tariff? Why we impose the tariff? So, first is the cost of the capital investment that any service provider is investing in the generation, the transmission and the distribution equipment. So, it must be recovered in the tariff. So, this is the first objective. Next is the cost of operation, supplies, maintenance and losses. It must be recovered from the customers. And then the cost of the metering, billing and collection, etc., that must also be recovered by the tariff. And also any person who is investing a capital, he or she must have to be a satisfactory net return on the capital cost. That should be that is a very important point, that is satisfactory net return on the capital cost must be ensured, and it should be simple and it should be comprehensive to the public, so that the public can easily understand that how I am charged the tariff. So, next is the general form of the tariff. What is the general form of a tariff? So, general form is A is equal to Cx plus dy plus f, where A is the total amount of the bill for a certain period. So, we can say A is the total amount of the bill, X is the maximum demand during the period. It may be in kVA or it may be in kilowatts. Some of the industries, they are using the maximum demand of kVA, and some of the industries, they are using the maximum demand of kilowatts. So, X is the maximum demand during any period, say any period of 1 month or 2 month or 6 month or 1 year accordingly. And Y is the total energy consumed during the period. So, for a specific period, how much energy is being consumed, that is in kilowatt hours. And next is C. C is the unit charge for the maximum demand in rupees, that on what basis so many rupees per kilowatt or so many rupees per kVA is charging for per unit kVA or per unit kilowatt. So, this is the unit charge and D is the unit cost of energy. It is in rupees per kilowatt hour. Say we are given nowadays that rupees 6 per kilowatt hour is the unit cost of the energy, and F are the constant charges. It is also given in rupees. So in the general form we can say that A, that is the total amount of bill for a certain period, is equal to the multiplication of unit charge for maximum demand and the maximum demand during the period, and plus the unit cost of energy and the total energy consumed during the period, and F are the constant charges. So next we are having the types of tariff. What are the various types we are dealing with the tariff? First is the flat demand rate, second is straight meter rate, third is the block meter rate, and fourth one is the Hopkinson demand rate, Dorothy rate, Wright demand rate, and the spot pricing. So these are the various types of tariffs we are implemented nowadays. So first is the flat demand rate. It can be expressed as that A is equal to Cx. In this part, the total amount of bill, that is depending upon only upon the maximum demand irrespective of the amount of energy consumed. That is the maximum demand, that was X, and C is the unit cost of the maximum demands. So this rate was very common to the irrigation tubers in the earlier days, where the load is fixed and the supply hours are fixed. So in this flat demand rate, we are not meant with the energy consumed in the particular time or in the particular section. So in this we are dealing with only with the maximum demand and the unit charge for the maximum demand. And nowadays it is used for the street lighting because they are having the fixed hours. They are being used for 6 or 7 hours or 8 hours, and they are having the fixed load. The load is not varying. So this is the flat demand rate. And second is the straight meter rate. So this tariff can be expressed as A is equal to dy. So the charges are depending only upon the amount of the energy used. How much energy is being used in a particular time and what is the rate of the energy. So the total bill depends upon the amount of energy into the number of the rate of the units. So it is sometimes used for the residential as well as for the commercial customers. It is having the advantage of simplicity, but it has one disadvantage, that if any customer doesn't use electricity during any period, he must not be charged for the minimum charges. He is getting the supply, he is getting the transformer over here in his premises, he is getting the wires in his premises, but he is not using the electricity for a particular time. So he is having the minimum bill. If he doesn't use any single unit in a month or in a particular period, he will not be charged any money. So this is the main disadvantage of the straight meter rate. And next is the block meter rate. So to remove the inconsistency of the straight meter rate, the block meter rate charges the customers on a sliding scale. So in this method, A is equal to d1y1 plus d2y2 plus d3y3 and so on. So in this method we are using that for the first block, say for the first part d1 and y1, we are considering that up to this much of the units, say up to 100 units, we are charging rupees 6 per kilowatt hour, and for the next 200 units we are charging rupees 7 per kilowatt hour, and for the further next units we are charging rupees 7 per unit. So this is called the block meter rate. In this, the D1, D2 and D3 are the unit charges for the energy and for the block of Y1 and Y2 and Y3 etc. In this method we are charging in the blocks. So if any customer is having smaller consumption, he or she must be charged accordingly, and if any customer is having large consumption, he or she must be charged accordingly. So this is the block meter rate. Next is the Hopkinson demand rate, or it can also be, it is also known as two-part tariff, and it is expressed as A is equal to Cx plus dy. So in this, the total bill includes a demand charge based on the maximum demand plus the charges based on the consumption of energy. Say in a particular period, any customer is having the maximum demand of 5 kilowatt, he or she must be charged accordingly plus the number of units consumed by the customer that are also to be included. In this, the flat demand rate, the disadvantage of flat demand rate is overcome, that is totally diminished in this method, the Hopkinson demand rate, because if any customer is not using electricity for a particular time, he will be charged accordingly, so that the connected load of 5 kilowatt or 4 kilowatt, that is to be charged by the that is charged by the utility. So this is called Hopkinson demand rate, or we can say it is two-part tariff. And next is the Dorothy rate, that it is also called the three-part tariff, and it can be expressed as A is equal to Cx plus dy plus F. So this tariff is generally used for the industrial customers. They are also having the maximum demand plus number of units plus the fixed charges. The fixed charges for a period, say for any industry, the maximum demand is 100 kilowatt, the rate of unit will be 6 or 7 rupees per kilowatt hour, and there are some fixed charges, fixed monthly charges or fixed charges for a particular time, for a particular period. So this is called three-part tariff or Dorothy rate. And then the right demand rate, in the right demand rate, it intensifies this inducement by lowering both the demand charges and the energy charges for a reduction in the maximum demand, that is by the improvement in the load factor. In this right demand rate, we are given that we know that during the nights the load is very low. So in this method we are given subsidies, or we can say that we are subsidizing the rate of electricity with that for this much of time. If we use the electricity for this much of time, we will given compensation, we are given the cheap electricity during that period, so that it can improve the load factor. So this tariff is generally specified for those industrial consumers who have control over their maximum demands. They can meet their requirements during the nights or during the off-peak hours. So this is called the right demand rate. Next is the spot pricing. Spot pricing, it is the price of electricity depends upon the time at which the consumption occurs, or the spot pricing rate, it can be written as spot price rate is equal to incremental operating cost plus the quality of supply component. So this is the spot pricing, we can given the rate at the on the spot. So next is the power factor. First of all, what is a power factor? So power factor of an AC electric power system, it can be defined as the ratio of the real power flowing to the load to the apparent power in the circuit, and it is a dimensionless number between 0 and 1. So real power is the capacity of the circuit for performing the work in a particular time. The apparent power is the product of the current and the voltage of the circuit, or we can say VI, or we can say kVA. So due to the energy stored in the load and returned to the source, or due to a non-linear load that distorts the wave shape of the current drawn from the source, the apparent power will be greater than the real power. So the ratio of real power to the apparent power, it is called the load factor, or we can say the angle between the voltage and the current is the cos of that angle, that is called the power factor. So, in the electrical power system, a load with a low power factor draws more current than a load with a high power factor for the same amount of useful power transferred. So, the higher the currents, increase the energy lost in the distribution system, and they require the larger wires and other equipment. So, if the power factor of any system becomes poor or the power factor of any system is low, then for the same rating, for the same power, we must have to use the bigger wires or the larger wires having large diameters and larger kVA rating transformers and larger generators. So, this is the effect of the low power factor because of the cost of larger equipment and the wasted energy. So, the electrical utilities will usually charge a higher cost to the industrial or the commercial customers where there is a low power factor because of they are having the higher energy cost. They must have to implement large equipment for the low power factor. So, if we can say that what is the power factor? Power factor is kilowatt or the real power divided by the kVA, that is the total power. So, if we can see this graph, that is kilowatt, that is the real power, and this is the apparent power kVA, and this is called, the green one is showing the kVAR, reactive power. So, the angle, there is some angle, it is having phi, and the cos of this phi, it is called the power factor. The angle, the cos of angle between the real power and apparent power, that is called the power factor, and these are the reactive power that is to be stored in the equipments. So, if we have to be more clear that the inductive loads cause the current to lag behind the voltage because the energy is being stored in the inductive loads because of their magnetizing properties. So, the waveforms of the voltage and current are then out of the phase with each other. The more out of phase they will become, then the lower the power factor. So, the power factor is usually expressed as that cos phi. So, now if we can see this example, the next lecture, next slide, that we can consider a canal boat, it being pulled by a horse. If the horse could walk on the water, then the angle phi would be 0, as we can see over here. If the horse can run on this water, but the horse cannot run on this water. So, if the horse can run on the water, then the power factor will be unity, but the cosine phi will be 0 and the cosine phi, that is equal to 1, meaning all the horsepower is being used to pull the load. However, the relative position of the horse influences the power. As the horse gets closer to the baggage, angle phi 1 increases and the power is wasted, but as the horse positioned further away, then the angle phi 2 gets closer to 0 and less power is wasted. As we can say, if the horse is over here, the more power will be wasted, but if the horse is coming just to the bank of the canal, then the full horsepower or almost maximum horsepower can be used to pull this boat. So, this is the fundamental for the power factor, that how it varies, what is the effect of the power factor. If we are having the poor power factor, we must have to use more power. So, now we are having the linear circuits. What a linear circuit is called? In a purely resistive AC circuit, where there is no inductance and no capacitance, we are having the purely resistive AC circuit. The voltage and current waveforms are in step or in phase, as in the next slide. So, this is the voltage waveform, the red one, and this is the current waveform. They are in phase to each other, and this is the power, and the average power is this one, with the green one it is showing. So we can say that in the linear circuits, the current and phase, they are the current and the voltage, they are in phase to each other. Their waveforms, they are falling on each other. Only the difference is of the magnitude, not of the phase angle. So in the purely resistive AC circuits, the voltage and current waveforms are in phase to each other and the changing the polarity at the same instant on the each cycle. So all the power entering the load is consumed, whereas the reactive loads are present. So where the reactive loads are present, as such with capacitors or inductors, energy stored in the loads result in the time difference between the current and voltage waveforms. So during the each cycle of the AC voltage, extra energy in addition to the energy consumed in the load is temporarily stored in the load in the electric or magnetic fields and then returned to the power grid for a fraction of second later in the cycle, as we can see. So this is the linear circuit starting from 0. This is the maximum negative 180 and then it is 0 again at 270, then it is at the maximum rate. So the voltage waveform and the current waveform, they are in the phase to each other, and this is the power waveform and this is the average power. So now we will deal that what is real and reactive power, what is the difference between these two. So the real power performs the actual work such as heating a burner element or illuminating an incandescent bulb. But the reactive power does not perform the work but energizes the magnetic fields in the motor windings or in the power supplies, which create the inductive loads. So this is the basic difference between the real power and the reactive power. So the real power, that performs actual work, but the reactive power just energizes the magnetic fields of the motor windings. So due to this reason, the power factor becomes poor, and the apparent power is the result of the combination of the real and reactive power. It measures the true load of an electrical distribution system. So we can say that the real power and reactive power, they are being used at the right angles, and the combination of the real and reactive power, it becomes the apparent power, or we can say the real power, VI. So we can say that what is the difference between the real and reactive power. So this is the real power. If we are having the resistive load, in the resistive load, this is the voltage waveform. The red one is the voltage waveform and the blue one is the current waveform. So in the resistive loads, the voltage and current, they are on the same waveform, they are having the same waveform, they are falling on each other. So we can say that the real power is this is the resistive load power, and then the reactive power. Reactive power is that it is the red one is the voltage waveform and the blue one is the current waveform. So in this, the inductive load, the current is lagging behind the reactive power by 90 degrees. So it is here we are shown that it is 90 degrees. The current waveform is shifted to 90 degrees from the voltage waveform. So this is the difference between the real and the reactive power. And then it is the power triangle we are having, that is the real power P, and this is the reactive power Q, and this is the apparent power. So when the real power and the reactive power they are used in combination, then the apparent power comes in the phase. So the angle between the real power and the apparent power, that is phi, and the cos of this angle is called the power factor. So now we can see what is the impact of the low power factor, what is the largest impact of the low power factor. So the low power factor causes the inefficient utilization of electrical power So, in other words, we can say that we are using more current to do the same amount of work when the power factor is low. So, if we take the basic equation for a single phase power, so we can say that the power is equal to volts into amperes into the power factor, and after solving it we can say that amperes is equal to power divided by volts and power factor. Now the power factor, the power will remain constant and the voltage will also remain constant. Now if the power factor becomes low, if this quantity will be lower, say we are having 100 volts, 10 amperes and zero point 0.8 power factors, then we are having 800 watts of power, and current will be 800 divided by 100 into this power factor 0.8. But if this current becomes low, if this power factor, this quantity becomes low, or we can say it becomes 0.6, this quantity will be increased, or we can say for doing the same work, for we have to use more current to do the same amount of work if the power factor is low. So this is the largest impact of the low power factor, that we must have to make more current for the same power. So this is the example that how low power factor affects the current. We are saying that we are having 100 kilowatts of real power and 100 watts of kVAR, and then the kVA becomes 141 kVA, this vector. So the cos phi is 100 divided by 141, that is 70%, or we can say that the power factor is 0.7. Now we are having that it is 100 kilowatt, again we are having the same real power, but now the reactive power is 32 kVAR. Instead of 100 kVAR, it is 32 kVAR. Now the kVA rating will be changed. There will be less kVA. Instead of 141 kVA, it is having 105 kVA. Now if we calculate the power factor, it is 100 divided by 105, it is 95%, or we can say the 0.95 power factor. And now if we have to see that how much current is required, 141, this much of kVA of the first system minus the kVA of the second system divided by the kVA, or we can say that 35% more current will be required if we are using 100 kVAR instead of 32 kVAR. So this is how the low power factor affects the current. For larger kVAR, we require larger current or larger kVA. Similarly, if we are having 100 kilowatt of real power and 141 kVA of the apparent power, then we must have to use larger transformers. As we can say that the kVA rating, there is a lot of difference between the kVA rating 105 and 141. So we can say that we must require larger transformers and larger generators if the kVAR rating is higher. So this is the example that how the low power factor affects the current. So it is given in the theory, that in the example on the left, power factor was measured at 70%, and if our goal is to produce 100 kilowatts of real power, we find that 141 kVA are required. Then the power triangle on the right, that shows a power factor of 95%. So in this instance, only 105 kVA are required to produce the same amount of real power. So since the voltage remains constant, the current must increase by 35% to deliver the desired power. So when the power factor is 70%. So we can see from here that if the power factor is 0.7 and it is improved to 0.95, we must require 35% less current. So 35% less current means we can use smaller wires, we can use smaller equipment for the same power. So next we are having what are the causes of the low power factor, why the power factor becomes low, what is the reason. So, the low power factor, it is caused mainly by the induction motors. As we know that the induction motor is the highest motor, almost 90